Okay, get ready. Here comes one of the most important lectures in this class. We got to talk about big carbon, study goal number 18. And this has implications for all sorts of ecology like we're doing now. This has implications for atmospheric stuff, climate change, ocean acidification. But in many ways, this is the basic chemical background for a whole bunch of your current socio-political and economic discussions. Um, the rest of your life will be very largely influenced by parts of today's lecture. So it's kind of a big one. You'll probably want to take a bunch of notes. And I'm going to try to keep it rather brief, expecting fully that you'll take pauses, that you'll make a lot of notes, and that you'll prepare questions so that you can ask me later. Okay? Um, it's tough for me to do this right now. It's late. I just made another cup of coffee. Um, I'm tired, and I imagine that some of you may have just woken up, and so I know it's tough to do this stuff. Let's make each other a truce. I'm going to pause in a minute, grab myself a little water, take a quick stretch, and you can take a quick pause, go grab a cup of coffee, make sure that you're awake before you do this lecture. So I'm going to pause here. And now that we've both had a chance to gather ourselves, quick review of study goal number 17. Remember that there's photosynthesis, cellular respiration. CO2, glucose are the carbon compounds on this screen. Plants do the photosynthesis part. They also do cellular respiration. You and I, we just eat their storage so that we can do the respiration part. And the only thing that I want to remind you beyond that is the energy storage concept. The fact that solar energy is used to create carbon bonds because breaking carbon bonds releases that energy. Okay, so now I want to quickly talk about some other types of carbon before you make the other drawings. There's a lot of carbon on Earth. There's this field called organic chemistry, which is just studying carbon compounds and carbon-based chemistry. Carbon is one of the big six, and so you probably know that all life is based on carbon chemistry. There's a bunch of carbon chemistry for you to know later in your science education. But for apes, you just need to know a couple of ingredients in each part of our planet. In the atmosphere, you should know carbon dioxide, and you should probably know methane, which is CH4. There's a whole bunch of other gases, but I think these are the big ones. In living things, we've already talked about glucose, sugar. Remember that there's other sugars too. There's all sorts of other carbon chemistry inside of life, but you should know lignin. I should have underlined that. I apologize. This right here should be underlined. That's lignin. Lignin is a really big compound. It's actually a category or a group of compounds. They're found in plants, and they're what make those rigid tubes, capillaries in plants. So that's one for you to know, lignin. And then the only other biotic carbon compound that I'm going to need you to know is calcium carbonate, CaCO3. Calcium carbonate is what our bones are made of. It's what puka sand is made of, or puka shells. Maybe you've seen those like bracelets or necklaces that people used to wear in the 80s that were like little pieces of seashell with a hole through them. Or maybe you've been to the tropics and you've seen that coarse, really white sand that's kind of crunchy, like when you walk, it makes a sound. Those are all calcium carbonate pieces left over. After shells die, after corals die, after things with bones die, all the flesh would rot off my body, but my bones would just stay breaking into smaller and smaller pieces of calcium carbonate. You might know calcium carbonate because Tums, like the antacid that some people eat when they have upset stomachs or whatever. Um, you might know calcium carbonate because if you leave a glass out for a long time, it'll start to get like little white crust on it. That includes calcium carbonate in that salt deposit on glass. So anyway, in life, we've got the sugars, the lignin, and the calcium carbonate. In water, we have carbonic acid, which is a weak acid, and carbonate ions. I wish I had a better explanation for you, but you should probably just write it down and move on. I'm sorry. It's the result of a bunch of other chemistry stuff. In rocks, um, carbon shows up in two different ways. These are both sedimentary types of rock. Either calcium carbonate stuff, like that puka sand, gets trapped in sediment and eventually becomes rock. Or living things can be trapped in sediment, and those become fossil fuels. That's usually single-celled stuff like algae, little tiny pieces of plant material, or plankton. But living stuff can be deposited into rock. And so here's what you get when you combine all of those ingredients that I just talked about. And make sure these are all in your notes before you switch screens. Here's all that carbon stuff happening at once. So for example, here's the biotic stuff. It's going from the atmosphere into living things. Remember, it might go into a plant. That plant might get eaten by an animal. There's the carbon stuff that we looked at earlier. But if we add mountains, for example, it's possible to assume that rainfall would carry some carbon out of rock into water. It's possible that rainfall would interact with carbon to make carbonic acid. It's possible that some amount of carbon could dissolve into water and end up in those plants. And it's possible that that could end up in fish. Here's your carbonic acid in the water, and here's various sediments. That's a lot of babble, but these are all places where you could find carbon in life. Now, quickly cycling through living things in the water. But here's where I need to start a distinction. Keep in mind that these things cycle pretty quickly, right? Like a plant might breathe out oxygen. I eat some lettuce and I breathe out some CO2. That CO2 goes into another plant. All that stuff could happen in minutes, theoretically. Carbon could dissolve into water, go into plants. Aquatic plants could put that into fish. Fish could exhale that carbon. It would come out of solution and go back to the air. This could be pretty fast too. But this stuff, like now that it's back into rock, once you've got carbon in rock, that's actually a pretty slow process. You know, the rock cycle, right? So once carbon is locked up as a sediment and becomes rock, that could be a really long time. You know, tectonic plates, right? So like sediment becomes sedimentary rock that takes gazillions of years, and then those tectonic plates are going to move around the planet very, very slowly. They're going to smash into each other. Sometimes there's some volcanic activity, sometimes they just get pushed up as mountains. That is slow stuff. So if we went back to this diagram, you might assume carbon spends a few minutes in the air, maybe a few hours. It might spend a few years in a tree if it's a big tree. It might spend a couple minutes in Jose if I eat some lettuce and then I go running right after or something. So pretty rapid life in the air, relatively rapid in life. Again, in water, you know, it could dissolve into water, become a seashell. That's pretty fast. But if little pieces of seashell or little pieces of life get trapped in sediment and become rock, now they're out of play. They've entered a really slow process. So really fast, pretty fast, but slow once it's in rocks. Little vocab thing. Remember that when rain wears away rocks, we call that weathering. And remember that when these types of carbon get stuck in rock, we call that a sink. A sink is a place where an element leaves the game. It's like when you lose when you lose like a single sock underneath the bed and you find it like 20 years later, that sock has like sunk out of your life. You like lose a fork behind the couch and like 5 years later, you're like, oh, there's that one fork. Same idea. Carbon is in the mix and it's in the mix and I'm using it and you're using it and lettuce is using it. And then if that little piece of me or that little piece of you or that little piece of lettuce gets stuck in rocks, well, no one's going to use that carbon for a long, long time. We say about 400 million years if you really want to know. So here comes this key distinction. Some carbon cycles fast. The biotic stuff, that includes the air, that includes the living things. There's a lot of carbon in soil. So like, you know, a beetle decomposes, carbon goes into little microbes, carbon gets off-gassed into the air. There's a lot of carbon in soil. There's a lot in shallow sediment. And remember, like in a shallow sediment, that's basically still life, right? Because there's like worms and crabs that pick through that. Some carbon in water. All of these are the fast stuff. But I want you to remember that when carbon enters the rock cycle, now we're talking slow. The average residency in rocks for carbon is maybe like 400 million years. It's a long, long time. P.S. Throwing in a little vocab term because I can. Lithification is when it becomes rock, when anything turns into rock, like it used to not be and now it is. Sand gets smushed and then chemistry starts to happen and all of a sudden it's not sand anymore, it's a rock. That's called lithification. You all know, like sandstone, like Lizard's Mouth, right? Like that used to be sand and then it like got squeezed and then some chemistry happened in the water and that loose sand under some heat and some pressure with some chemistry happening becomes rock. That's lithification, okay? You know, if you think about it, like how does carbon ever come out of rocks? These aren't like regular events that are happening all the time. You could look at a rock all day and never notice it weathering. And like if you consider how big the planet is, it's not like rocks are dissolving all the time, right? Like the only ways that rock carbon can leave is if this mountain explodes into gases, volcano, or if this mountain gets worn away by rainfall. But that's all nickel and dime, right? That's usually really slow and gradual and small potatoes. So we've got this fast carbon. That's the day-to-day carbon, what we have in play, the biotic stuff, the life stuff. And then we've got the slow carbon. That's like carbon that has sunk, carbon that has gone into rock. Once that stuff's in rock, that's going to be in rock forever. And, you know, sediment becomes rock little bit at a time over long periods of time. Rock stops being rock over long periods of time, little bit at a time, right? Unless. Make sure you've taken all the notes you need because things are about to get pretty different now. Unless. Unless we figured out a way to speed up the rock cycle. Right? Like if you consider how much carbon is in rocks and how much our planet has of carbon in rock, that's a lot of carbon. And like every bazillion years, one volcano goes and like, oh, hey, look, we got a little bit new carbon, but that's chunk change, right? And then like rocks weathering, like you would never see that. You could just watch rocks dissolving the rest of your life and never see them look any different because that's just little tiny bits of carbon, right? But get this crazy idea. Some wacky person figured out that you can drill a hole down through the rocks and you can find a whole bunch of carbon bonds down there sometimes. We call those fossil fuels. And we get that energy out just like this. You know how you break carbon bonds and get energy? Well, what if we could find a whole bunch of carbon bonds? Well, that would just release the energy it takes to drive this vehicle, and then that would put more carbon into the air, right? Humans have basically become a gigantic, all the time, 24/7 volcano. I'll explain more, don't worry. Crazy idea is that there are some rocks out there that we can light on fire to get energy out, like coal, or some rocks that are kind of syrupy, and if we do some weird stuff to that syrupy stuff, we can make it really runny, you know. And then you can put that stuff in your car, and inside your engine, there's like these little sparks, and like all these carbon bonds are being broken. It's a lot. It's like, you know, a full day's worth of human energy. Every like, what is it, 1 ounce of gasoline is like a human day's energy total. That's like a lot of carbon bonds. Like 2,000 calories that I might take to run my body in 1 day. There's like 16 days worth of that in 1 gallon of gasoline. That's a lot of energy. So it makes sense, right? Here's another perfectly rational decision. Humans figured out that we can find some of these rocks, light them on fire, do some wacky chemistry, and get all the energy out of those carbon bonds. I mean, if we found that there was rocks with a whole bunch of like strawberries in there, we'd be like, hooray, we found all this sugar. Like, that'd be nice, right? We'd all be happy to eat strawberries. Instead, we found all these rocks that have like hell of energy, like unbelievable amounts of carbon bonds. You know, the sun was shining like 500 million years ago, and a whole region of the ocean was making algae that was settling down to the sediment and something wacky happened around 500 million years ago in that area, where like maybe some sand covered up all that algae, and it just became like boop, like a huge glob of carbon bonds. And it's been sitting there, basically ignored for 500 million years. And some random human was like, huh, you can light that stuff on fire and get all that energy out. So we've been doing that. We've been getting all the energy out of the rocks for like 150 years now. That's crazy. That's really interesting, because here's what happens when we dig up the rocks and we light them on fire. We're releasing CO2, a lot of it, like crazy amounts. So if you don't mind, I'm going to go back to this screen, and I'm going to try to write something on here. Okay, I'm going to see if this works. You'll have to forgive me. I really don't have a lot of faith in this technology. Let's see if this will work, okay? This is slow. Sorry, I'm so tired. Oh man, now I'm messing everything up. That's not slow. This is relatively fast. Excuse me. This is slow. You know, where carbon becomes rocks. And this is slow, where carbon leaves the rocks. It either leaves dissolved by rainfall, or it leaves, you know, when those mountains occasionally become a volcano. Neat volcano. Now here's the one thing that's fascinating. We have accelerated this part, like tremendously so. Like we are taking all this stuff and we're turning it into gas form. And in terms of geology, we've done that extremely fast. Like double X fast, maybe quadruple X fast. Like really, really, really fast. You know, like in the last 70 years, our burning of fossil fuels has put more carbon into the atmosphere than something like 400,000 years worth of volcanoes. And it's not like rocks are being made any faster. We're just adding more carbon in one place. Like this part where carbon becomes rock, that's still slow. Like, check, no change there, right? Like sediments are just depositing in the bottom of the ocean at the same rate that they always have, more or less. And you know, this slow process still happens, right? Like there's still volcanoes and there's still rainfall. Like that's all happening. We still have like plants doing the plant thing, and we still have animals doing the animal thing. We still have like acid in the ocean. We still have like all this is fine, but we're just adding one new thing to carbon. The new thing is we're hacking the rock cycle on one half. We're not hacking this part of the rock cycle. We're hacking this part where we are taking old carbon that would have been in a slow release, and we've accelerated the release of that old slow carbon. We now have extra carbon. I don't want to be too alarmist about this, but pretty much that's the biggest problem for your entire generation. Like, population stuff, resource stuff, water stuff. There's a lot of things we could talk about. Biodiversity is kind of depressing. Collapsing fisheries are kind of sad. Smog, air pollution, carcinogens. There's a lot of problems. But the big one is that humans are like this big dumb volcano that like keeps volcanoing, and like every day you and I are like driving around in our cars like doop 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 doop, and like life is good, but you know we are part of this giant volcano that just keeps going off every day, taking all this rock carbon that should have been in long-term storage, and we're just like just adding that stuff into the atmosphere. That's nutty, and that's creating a lot of our topics of discussion in this class. So I'm kind of glad we could do this today. Okay, I think I will probably stop here. Hit me up with questions. I hope I didn't babble too much. I also know I got a little confused when I wrote slow instead of fast. Okay.